Welcome back. Let us continue the discussion on coupling of chemical kinetics and the thermodynamics. So, what we are in the middle of doing the discussion, we are looking some basic reactors and then doing the analysis. So, based on their assumption and other characteristics. So, the last one where we stopped while doing the plug flow reactor. So, this is where we started off. This is the schematic of the plug flow reactor, where the species comes in and then goes out. This is the control volume, small control volume, and then everything here there are some assumptions which it is built upon: steady state, steady flow, no axial mixing and all this. Then what we are doing, there are basic conservation equation of mass conservation. So, this is the small element that we have taken, and mass conservation, then momentum conservation, and momentum only we are looking at the x momentum, and then energy also, where this is the energy flux comes in, that goes out, and the species mass transfer. So, this we can look at the system with all the. So, this is the picture. If you recall that these are the fundamental equations, where x momentum, energy, species, how many number of equations, mass has n, equation of state 1, calorific equation of. So, using this concept we started this set of equation, and then finally, we derived and we stopped here, where you get dp dx in terms of some coefficients a and b, and obviously, the other parameters like axial velocity, thermodynamic parameter, temperature, Cp and all these are there, where a is like this and b is represented like this. Now, we can look at the temperature gradient. So, that would look like now V x square by rho Cp d rho by dx plus V x square by Cp 1 by A dA by dx. So, minus we have one term which is 1 by V x rho Cp summation over all the species H I omega dot I molecular weight of I. So, this is your equation number 52, and the species conservation equation will comes down to this omega dot I molecular weight of I rho V x. So, this would be your equation number 53. So, what you can note here in this particular equation. So, there q double prime, this has been set to 0. This is for simplification. So, for simplification, that has been. Now, one can calculate the residence time. So, which adds one more equation. When you look at the residence time, this would be derivative of r with respect to x 1 by V x. So, that is the residence time. Now, there are initial conditions. So, the equations 5.51 to 54, there are initial conditions which are essentially required to solve this equation. This is T naught, density will be rho naught, y I is y I naught for I equals to 1 to n, and Tr is 0. So, this is your sets of equation from A to T. So, these are the initial conditions which all the above equation they are exposed to, and rather those equations can be solved based on these initial conditions. Now, once you have the initial condition, you can easily find out this solution of these ODEs, because these are simple ODEs. So, using this one can find out the solution of these ODEs, and that will get you the temperature profile, species profile and other things. Now, we can look at some of this application of the to the combustion system modeling, where we actually apply these things, because what we looked at is the basic fundamental reactors like plug flow reactor, perfectly stirred reactor, constant volume reactor, constant pressure reactor. So, where do we use all this? So, now the combination of well stirred reactor and plug flow reactors can be used to approximate more complex combustion system. For example, you have a fuel and this is air. Now, this is one of the well stirred reactor. WSR stands for well stirred reactor, well stirred reactor. So, this is the first WSR, then there is a recycling or fuel comes in, air comes in, some combustion product comes out, it gets into second well stirred reactor, where again some amount of fuel and some amount of air goes in along with this combustion product. So, that means there are 3 inlet, again some amount of fresh fuel is coming in, some amount of fresh air is coming in and the combustion product. Then finally, this combustion product goes to plug flow reactor. So, this is plug flow reactor, and then finally, you get the final set of products. Now, you look at a slightly complicated example of gas turbine, where you have so many different regime of thing. So, this is an schematic or the cut section of a gas turbine combustor. So, if you look at this is the outer casing or rather air casing. First portion here is the diffuser. So, in the diffuser actually if you look at realistically while flying, then you can see there is a fan also there which sucks in the air to the system. Then you have a fuel nozzle and some other cover shroud and the swirler. So, the air comes in here, that is allowed to pass through this swirler. So, when that pass through this swirler, what it does, it actually imparts tangential momentum to the air. And also, so essentially when you put so many the energy to it, so there will be pure 3 dimensional. This does lot of things. It not only allows to have rapid quick mixing, also make the system more turbulent in nature. So, there is a very specific purpose of using this kind of swirler, and then the fuel comes in, so that gets well mixed. If it is a liquid fuel, then that will atomize and evaporate, and then the air is there. So, the primary zone, there would be primary reaction going on. So, this is called the primary zone. Then these are the primary holes, where again the air is passed through, and these are the liner, and these are the secondary hole, where the secondary hole allows some more air to come in, because also the some air which is bypassed there, that goes through these casings and they goes through these holes. Now, secondary airs when it comes through, they also take part in the secondary combustion or in the secondary zone combustion. So, whatever comes out from this side, this will also react with the excess air, which is there are two purposes of say injecting the secondary injection, or rather having the secondary injection. It will not only allow to have some reaction to take place if there is some excess fuel. So, that would be burned here, because now you inject some more air to it. Secondly, it will also mix with the hot product and little bit smooth out the temperature profile, so that when it goes out, and that is also done through other dilution hole also. So, at the end of this, at the outlet, the idea is that one needs to, or the expectation is that the temperature profile here at the outlet, the T profile should be smooth enough. So, that is the whole idea, and to get that we do lot of dilution, primary secondary injections. So, that I mean also there are other advantages of doing this multiple injections through these things, but end of the day what one wants to have it a smoother T profile. So, once you have a smoother T profile, this will reduces your pattern factor, and that is one of the biggest design concern for gas turbine engine. So, that is because this temperature outlet of the combustion product, that actually goes to turbine. So, turbine has an, I mean that we have already discussed, turbine is the, in a gas turbine engine, turbine plays a critical role, because that dictates the rest of the design issues. Now, how we model these things? It is modeled as two well stirred reactor and a plug flow reactor. So, where are the well stirred reactor? The primary zone is one of the well stirred reactor. So, primary zone with recirculation of the combustion product, this is one well stirred reactor, and the second well stirred reactor would be sitting in the. So, if you go back to this schematic, this is where air comes in, fuel comes in. So, they react, the recycling is essentially nothing but that because of the swelling, flow, recirculation bubbles, things bring back. So, this is one well stirred reactor, then you add some more fuel, and this is second well stirred reactor, and finally, the plug flow reactor in the dilution zone. So, this reactor modeling approach are often used as complementary to the tools for more sophisticated final element or different numerical models for combustion chamber. So, these are some these things that one used to simplify a complicated problem like an gas turbine engine. So, that actually gives you an idea, this application of these basic or fundamental reactors for the modeling purposes of the complicated system. So, though it is simplified system, that can give you a fair amount of idea what goes on in the system. So, that pretty much actually we want to talk about the coupling thing, and then we will move to the next set of discussion, which will essentially, because now we have finished all these basics of the combustion and all these things, basic thermodynamics, basic properties, and now we will go to a very specific thing, premix flame. So, and laminar premix flame. So, that means this talks about two things. One is the premixed, that means my fuel and air. So, this gives me an idea that fuel and air, they are already mixed. So, that means they are mixed a priori and then sent to the reacting zone or combustion zone or combustor. Laminar stands for because this is from your fluid mechanics. So, the flow is laminar. So, essentially your this immediately tells you, as soon as you say laminar premix, that means you can get some idea about the scales and all these things. So, let us go into that discussion. Now, there are certain important properties that one has to know before getting into the details of these premix flames. So, one is that the premix flame is self sustaining propagation of a localized combustion zone at subsonic velocities. So, this is an important point. So, that actually now we call it sometimes the deflagration in gas dynamics or compressible gas dynamics, or to define a premix flame traveling at subsonic speed. Now, if you consider a premixed flammable mixture in a long tube open at both ends, that means we are talking about this kind of a tube which is open at both ends, and you have a premixed mixture here, and you ignite from one end, then the combustion wave which will be generated due to this reaction, that will travel down to the tube towards the other end from the starting point. Now, more to it, the flame is caused by a self propagating exothermic reaction which is accompanied by a reaction zone. That means, when this premix mixture is ignited, the combustion wave will travel towards the other side, then obviously it will create some sort of an. So, if it is passing through this tube, somewhere it will create an thin reaction zone. So, one side of that would be burned side, other side would be unburned side. That means, mixture comes in. So, that it is a self sustaining or self propagating system. Now, it will propagate through a stationary gas mixture at a characteristic velocity which is called burning velocity or laminar flame speed. So, this is one of the very fundamental property of a premix flame, and that one has to know. Now, most hydrocarbon stoichiometric mixture does velocity about this. So, that we will see how this burning velocity actually varies with the mixture, or rather the stoichiometric mixture coefficient. Now, when you talk about, these are some essentially the comments. When you talk about hydrogen air mixture compared to a hydrocarbon fuel, this burning velocity is quite higher, and that happens because once we will do the detailed analysis of this burning velocity, we will see that depends on the molecular weight, I mean along with the mass diffusivity, and hydrogen has much higher mass diffusivity. Now, the velocity of this wave is also controlled by the diffusion of heat and active radicals. That is always obvious, because once the reaction starts in any reacting system, there would be formation of radicals and active radicals, and that will also, I mean, produce some heat. Now, when the flame is burning in a mixture of gases, then the pressure and composition, two characteristic properties can be defined and measured. One is the burning velocity or flame speed or laminar flame speed, second is the flame temperature. So, now that is always obvious. Now, when there is a reaction going on, obviously we will have a temperature, because these are mostly exothermic reaction, and any exothermic reaction there will be heat release. So, when there is a heat release, we would be able to get some temperature. So, that one may think about, there is what is something very I mean fancy about it. I mean, we will see when you talk about the premix mixture, it is slightly different, and that is why flame temperature is always obvious, but the important thing is the burning velocity and also flame thickness, which will come to that. So, the temperature you can predict from the thermodynamic data, and if you invoke also chemical equilibrium concept, you can do that. And secondly, the prediction of the burning velocity, people have predicted that thing through lot of experimental observation, there are theoretical models, and So, lot of things which are present there for prediction of the burning velocity. Now, to go back little bit to the history, there are essentially two approaches formulating the laminar flame propagation in premixed gases. First one, there is a hypothesis on which talks about thermal propagation. That means, the mixture is heated by conduction to the point where the rate of reaction is sufficiently rapid to become self propagating. So, that is a concept completely based on thermal analogy, and the second one based on the diffusional propagation, which talks about that diffusion of active species such as atoms and radicals from the reaction zone or the burned gas into the unreacted mixture causes reaction to occur. So, there are two different thought process completely. One is purely based on the thermal hypothesis, that there is a, I mean, if you look at the system like this, and this is the reaction zone, this is unburned, this is burned. From here, this side the heat transfer takes place. Due to the heat transfer, so this gets again ignited or the burning takes place. Or the other case, the diffusion approach is that from here the active radical or atoms or species diffuse through the unburned side. So, in reality what happens is diffusion of heat and active radicals both are essentially there, because when there is an unburned mixture from this side, in obvious situation there will be heat transfer to the unburned mixture, and there will be also some transfer or the diffusion of the active radicals, which will do take part in the process. Now, this is a picture of a freely propagating premixed flame. So, this is very standard picture and available in any textbook, and what it shows that this is the initial mixture which is at the lower temperature. So, as it goes along, this reaches a final temperature. This is your burnt temperature. That means, the other side of the reaction zone. If this is the, so if this is the flame thickness, this is my burnt side, this is unburnt side, and when the temperature goes up due to reaction, the reactants will also automatically gets consumed. So, this is my starting point of the reactants at the initial stage, and as it getting consumed, it will come down and it completely consumes it. So, that is how happens to the reactants, and once the reactants are getting consumed, obviously we start getting the product. So, this is where the products are. So, one end, so this is very standard situation when there is a reaction zone, some reactants will be consumed. So, that concentration or mass would come down, obviously the product formation is there. So, that will go up. Now, in between that there are some intermediates, these are intermediate, this will be radical or species or atom, whatever that form. Now, if you divide this whole picture, so this side of this dotted line, this is a cold reactant zone. That means, here at this inlet, if this is my T naught condition, so this is all reactants are at the cold condition. So, that means they are not getting into the business. Then as the things move along, this particular zone called the prim flame zone, where slowly the reactants are getting heated up because of the temperature increase and all this, and finally this is the zone which is visible flame zone, and this whole zone from this dot to this called the reaction zone, and in the reaction zone you can see the abrupt changes of this reactant species which gets consumed completely, product species are formed, there is a intermediate species which are also formed, and the temperature goes up, and finally this side of this is the product zones, because you have only the temperature of the burnt product and you get these things. So, one can do some simplified analysis here. Whole idea is to find out the some simple analytical expression for the laminar flame speed or laminar burning velocity, whatever we call it. So, to do that, any simplified analysis will obviously have some assumption. First is 1D constant area steady flow, that is number 1. So, then all your kinetic energies, potential energies, viscous effect, thermal radiation, these are all neglected. So, that is number 2. Also, across the flame pressure is assumed to be constant. So, that means there is no change in pressure, or rather pressure is not becoming an active parameter to contribute to that. And diffusion of heat and mass, these are governed by the diffusion law like Fourier's law and Fick's law. Then one more thing, which another, this is a non-dimensional number called Lewis number, which is a ratio between alpha and d. It is a thermal diffusivity to mass diffusivity, or one can write in terms of kappa by rho Cp d. So, the Lewis number is 1. That means thermal diffusion and mass diffusion are occurring at the same rate. If it is 1, that means thermal diffusivity and mass diffusivity are of the same order. So, that where it helps, because that simplifies the energy equation. Okay. Now, individual Cp values are all equal and constant. So, if you take some species, the Cp values are all equal and constant. Then kinetics, which is important, because when we are talking about the reaction and all these things, so we have to take into consider the kinetics. So, this is a single step, that means it is a simplified already, which is essentially sort of an global kinetics exothermic reaction, and we take a condition which is a lean condition, that means the fuel is completely consumed. So, which is not an rich condition. Now, if we look at the picture, so this is how we define, this is my, we said one dimensional. So, this is a one directional coordinate system. We take a small infinitesimal distance in that flame front, that is delta x. This is the amount of reactant mass coming in. I mean, essentially this is my control volume, and this is the temperature rise which will be. So, anything that we will get, this will be all function of x only, because this is assumed to be one dimensional. So, important conclusions are, it is 1D constant area steady flow, any other kinetic and potential energy, these are neglected. Then thermal diffusion and mass diffusion are occurring at the same rate, and individual Cp values are equal, and the reaction is one step global kinetics. So, that is how we define it. So, this is where we start our analysis, but we will stop it here and we will continue this analysis in the next lecture. Thank you.